2,000 years ago, in an ancient temple, there was a metal sphere. It spun on jets of steam. That was the Aeolipile, the world's first steam engine. A device of genius. It could have rewritten history, but it didn't. It never powered factories. It never moved trains. This was centuries before the Industrial Revolution. So the question is, why? What was missing from that advanced society? What crucial ingredient? And what does its quiet fate tell us about our own technological dreams? How do you define a revolutionary idea? What are the hidden rules, the rules that decide whether an invention changes the world or just gathers dust? Hero of Alexandria, that's the name, 1st century near the library. He was a thinker, a tinkerer, scrolls and steam, gears and curiosity. He wrote a book, Pneumatica, a catalogue of wonders, temple doors that opened on their own from an altar fire, a coin machine for holy water, and in there, the details for that spinning sphere. The Aeolipile, for him, it wasn't an engine, not like we think. It was a demonstration, a physical proof, showing the power of heated air and steam, action and reaction. Answering a philosophical question with a whirling metal toy, his society saw these as wonders, clever tricks for temples and gardens, symbols of ingenuity, not tools for changing life. Historians, James McClellan for one, mark this as a key point. The Hellenistic world had an advanced engineering culture. They could calculate the mechanics of a steam jet. But that culture put its genius in a specific box, the box of demonstration, of spectacle, of natural philosophy. The machine proved an idea about the world. It didn't have a job to do in the world, so that's the first clue. The spark was there, the technical knowledge was astonishing, but the mindset was different. The question wasn't what can this build or how can this lift a burden. The question was what does this reveal about nature's secrets, and that's where the story turns. The first crucial turn away from the path you might expect. The motion comes from a basic truth. Every action has an equal and opposite reaction. Isaac Newton would later write that law into physics. But Hero of Alexandria saw it in steam. To understand the Aeolipile, you have to picture it, a hollow bronze sphere mounted on hollow pipes that act as an axle. Those pipes connect to a sealed cauldron of water below, sitting over a fire. The fire heats the water until it boils. Steam rises through the pipes and fills the sphere. Now, on opposite sides of that sphere, there are two more pipes, bent at sharp angles like elbows. They're the only exits, so the pressurized steam rushes out of these bent nozzles, shooting straight out. And that's where the law takes over. The steam jet pushing out one way creates a force pushing the sphere the other way. With two jets firing on opposite tangents, the sphere is pushed into a spin. It's the same principle that makes a rotary lawn sprinkler turn. Water shoots out of bent arms and the sprinkler head whirls around. The Aeolipile was a steam-powered sprinkler head. A beautiful demonstration of a fundamental force, but that elegance had limits. The materials, the heating method, an open flame under a bronze pot meant it could never build high pressure. The spinning sphere produced very little torque. That's the twisting force needed to do actual work. It could spin freely on its bearings, a mesmerizing display. But if you tried to connect it to a grindstone or a pump or a mill, that delicate motion would stop. It was a captive force, impressive to watch, but incapable of lifting a load or driving a machine. And that's the first concrete clue to its fate. Hero discovered a revolutionary principle, but he built a device that could only demonstrate that principle, not apply it. The gap between a fascinating idea and a practical tool was vast, and it was built right into the machine's mechanics. The sphere was a captive force. But so was the imagination of its time. To understand that, you look at who was watching it spin. the audience wasn't a factory owner, it wasn't a merchant. It was the educated elite, the philosophers, the temple priests. For them, the world of making things, of building, was separate from the world of thinking. Manual labor was often seen as beneath the refined citizen. True knowledge was about contemplating nature's laws, not about bending them to some mundane task. So when Hero presented his Aeolipile, he called it a automata, a wonder, a marvel. It belonged with automatic temple doors or a mechanical singing bird. Its purpose was to inspire awe, to provoke a discussion about air and fire. It was a demonstration of human cleverness, a celebration of the mind's power to mimic nature's hidden forces. The Roman philosopher Seneca wrote about a similar device. He captured that spirit. He didn't wonder about its industrial potential. He saw it as proof. Proof that even the great forces of the world, wind and storm, could be understood, replicated in miniature. The engine was a philosophical toy, a conversation piece for a symposium. That cultural lens is critical. There was no concept that valued technological progress for its own sake, as a driver of economic production or broad social change. The idea of an invention improving the lot of common people through mechanized work, that simply wasn't a central goal. The engine was a brilliant answer. But it was an answer to a question their society wasn't asking. What if we could make labor easier? What if we could make production faster? That question would have to wait. For a different world with a different set of pressures, and those pressures, it turns out, were deeply economic. The leisurely pace of philosophical wonder had a foundation. A very specific, very rigid economic foundation. One that actively discouraged the kind of innovation the Aeolipile hinted at. That economic foundation wasn't just a philosophy. It was a practical reality. The engine of the ancient economy was human muscle. Everything ran on it. The big farms, the public projects, even work in the home. All of it needed a huge, available workforce, and slavery was a central pillar of that. It was a flexible source of power. From an owner's view, it was renewable. This created a powerful economic disincentive, one we often miss today. Why would a wealthy landowner invest a huge amount of capital into a complex metal machine? A machine that needed skilled metal workers. It needed constant fuel. It would probably break down under strain, when the alternative was a group of people. People you could direct to dig a canal or lift stones or grind grain with simple tools. The cost-benefit analysis was stark. The initial investment for a steam pump would be enormous. The risk of failure was high, but buying and maintaining a labor force that was a familiar expense. It was predictable. There was no real economic pressure to invent labor-saving technology. No market signal screaming for efficiency. No rising wages for free workers creating a financial squeeze. The forces that drove Britain's industrial surge later on, they were absent here. The need to pump water from deep coal mines, that demand wasn't there. Here, the demand was for steady output, controllable output, not revolutionary leaps in productivity. So the flash of the Aeolipile faded, not because people were unimpressed, but because society had no concrete place to use it. The socket for that kind of power hadn't been invented yet. And that leads to the silent partners of any revolution, the unglamorous technologies that need to be in place first for a great idea to catch fire. The missing link wasn't just a mindset, it was the material. The ancient world's genius was locked in bronze. To go from a philosophical toy to an industrial workhorse required a different kind of magic. Metallurgy, precision. A real steam engine is a pressure vessel. It has to contain an incredible force, the explosion of boiling water directed. For that, you need metal. Strong metal, uniform, predictable. The Romans built with iron, but their main product was wrought iron, forged by hand, hammered into shape. It was tough. But it could be inconsistent, not ideal for casting large, complex parts. parts that have to be perfectly sealed. The breakthrough material later was refined cast iron. Molten iron poured into sand molds to create solid, dense shapes, cylinders, pistons, boilers. That process, perfected over centuries, allowed for mass production of strong, intricate parts. The ancient world cast bronze beautifully for statues, for the Aeolipile sphere itself, but bronze is expensive, copper and tin. Iron was the common metal, the everyday metal, and they hadn't yet mastered the high-temperature furnaces, the precise chemical control to cast it reliably on an industrial scale. So the material foundation for a high-pressure machine, it just wasn't there. Imagine building a modern car engine from hand-hammered copper plates. The idea is there. The substance fails. That's the first half of the trap. The second half is more subtle. It's the gap of precision. A steam engine's power comes from a piston moving inside a cylinder. The fit has to be almost perfect. Too loose, steam leaks out. Power is lost. Too tight, the metal seizes. It grinds to a halt. Achieving that fit requires the ability to measure with incredible accuracy, and to machine metal to those measurements. This is where a simple tool becomes revolutionary: the screw-cutting lathe. In the 18th century, this device let engineers cut perfectly threaded screws. Those screws could then be used in other machines to apply precise, controlled force, to bore a cylinder straight and smooth, to create valves that open and close with exact timing. The ancient world had lathes, but they were for wood or for shaping the outside of metal objects. The concept of using a machine to create other machines with interchangeable precision parts, that was the seed of industrialization. Without it, every cylinder and piston is a one-off masterpiece, hand-fitted by a supremely skilled artisan. You could never standardize, you could never scale up. The Aeolipile was made of thin sheet metal. It spun at the pressure of a steaming kettle, a beautiful demonstration. But to scale it into a machine that could pump water from a mine or drive a loom, you'd need to contain pressures dozens of times higher. The bronze sphere would have torn itself apart, so the dream of steam power remained a dream, not for lack of imagination, for lack of a specific, mundane toolkit. It shows you something about innovation. A great idea often isn't enough. It has to wait for a whole ecosystem of lesser-known practical technologies to mature. The enabling technologies, the unsung heroes, and this technological gap points to a deeper question about knowledge in the ancient world. How did they pursue understanding? Was their science, brilliant as it was, structured in a way that could bridge such a practical gap? The steam was a spirit. It was pneuma to them, the world's breath. A living principle. They saw its force, they marveled, but they didn't have the language, they didn't have the framework to ask the next question. How much work can this breath do? Can we measure its strength, compare it to a man or an ox, and calculate an improvement? That question belonged to a science that didn't exist yet: thermodynamics. The study of heat and work and energy. The ancient world was a master of practical mechanics. They built aqueducts that defied gravity. They calculated leverage to move colossal stones. They understood statics, the science of objects at rest, but the science of objects in motion, driven by heat. That was a different frontier. They lacked the core concepts. The relationship between a gas's pressure and its volume. The idea that heat could be converted systematically into mechanical work. The notion of efficiency. Measuring how much useful motion you could get from a given amount of fuel. Without that framework, the Aeolipile remained an isolated wonder, an empirical discovery. You heat water in a sealed vessel and something interesting happens, but why it happened and how to make it happen better, stronger, more usefully, that path wasn't clear. There was no research program for improving heat engines. No community of engineers sharing findings on boiler designs or piston seals. The device was a brilliant end point, not a stepping stone. This separation is profound. It shows how knowledge can be deep in one area and absent in another. They could build a complex geared calendar, the Antikythera mechanism, tracking celestial cycles with precision. Yet the systematic study of the power in a boiling pot eluded them. The potential of steam was locked away by a missing chapter in the book of science. A chapter that wouldn't be written for another 1700 years. And this pattern, this fate of a brilliant device leading nowhere, it wasn't unique to the steam sphere. It was the story of an entire era. Hero's Workshop was this collection of strange devices. The spinning steam sphere was just one of them. There was a water clock that kept perfect time just from a steady drip. There were these little automatic theaters, whole plays performed by tiny figures, all run by hidden weights and strings and siphons. Temple doors that swung open by themselves when a priest lit a fire, using the air expanding from the heat. These were masterpieces, hydraulics, pneumatics, complex systems that showed a real understanding of mechanics, but they all had the same purpose. They were for spectacle. For ritual, for measurement, not for making things. They solved problems of ceremony or philosophy, not problems of work or transport. Then there's the best example. The Antikythera mechanism, found in a shipwreck over a century ago. It was just a corroded bronze lump, a puzzle for decades, but modern imaging showed what it really is. It's an ancient Greek astronomical computer, 30 interlocking bronze gears inside a wooden case. You'd turn a hand crank, and it would calculate the positions of the sun and moon, predict eclipses, even track the cycles of the Olympic Games. It modeled the irregular motions of the heavens with a precision that wouldn't be matched for 1,000 years. It's probably the most sophisticated mechanical artifact from the ancient world, a testament to a level of craftsmanship and knowledge that stuns historians. Yet it also led nowhere. It was a singular achievement, a tool for an astronomer or a philosopher, maybe a wealthy patron. There's no evidence of a second one. No school of gear making that grew from it, no industry of personal celestial calculators. It was an endpoint, a breathtaking demonstration of what was possible, built for a very specific, very narrow purpose. So you see a pattern: the steam engine that didn't power anything, the computer that didn't compute for commerce, the automatic plays that didn't automate work. These weren't failures of ingenuity. They were triumphs of a particular kind. They were solutions crafted within the boundaries of their society's questions. And the questions were about understanding the cosmos, honoring the gods, displaying wealth and wisdom, the drive to mechanize for economic gain, to save human effort on a massive scale. That just wasn't the force behind it. These marvels prove the capability was there, the minds were there, the skilled hands were there. What was missing was the context, the economic pressure, the social need, and maybe most practically of all, the right kind of energy. All these devices, for all their complexity, ran on simple power: a hand crank, a falling weight, a trickle of water. Even the Aeolipile's fire was just a small flame under a pot. To jump from these exquisite demonstrations to an industrial revolution requires a fuel source. One that's abundant, concentrated, portable. A fuel you can mine, transport, and burn in vast quantities to generate truly transformative power. The ancient world had a candidate right beneath their feet. But they never saw it as the key to a new age. Coal was more of a curiosity, not a cornerstone. The ancient world knew it was there. In Roman Britain, you could find lumps of it on beaches in shallow seams. They'd use it in small forges for heating, even in burials, but it was a local thing, a supplement. It never became the lifeblood. There were no deep mines for it. No canal networks full of barges, no cities under its smoke. The main fuel was wood and charcoal, which is wood refined. Think of a landscape powered by forests. Wood heated the floors of Roman villas. Charcoal gave you the hot, clean flame for smelting metal. It was a sophisticated system, but it had a limit. It was diffuse. A charcoal burner needed huge areas of woodland. The fuel itself was bulky, hard to move far. Your energy was tied to where the forests were. That meant a decentralized energy economy. A blacksmith's forge, a bathhouse, a kiln. Each one drew from the local woods that worked for a society of artisans. For small-scale production, but it could never concentrate the energy you'd need for an industrial revolution. Imagine trying to run a house-sized steam engine day and night on cartloads of charcoal. The logistics would be impossible. You'd strip the forest in months. The energy return wasn't there. You'd spend more effort getting the fuel than the machine could give you back in work. That's the practical reason the Aeolipile stayed a toy. To make it matter, you'd have to feed it, and the ancient world's pantry didn't have that kind of fuel. Now look at Britain centuries later. The birthplace of the steam engine wasn't a garden. It was a coal mine. The deep, flooded mines in Cornwall. Miners dug deeper for coal and hit water. The mines flooded. That was a crisis, an economic threat. The fuel was there, but they couldn't reach it. That created a desperate demand, a reward for anyone who could pump the water out. That demand is what turned steam into a practical machine. Thomas Newcomen built his engine in the early 1700s for one job: pumping water from mines. It was inefficient, but it burned the coal that was right there at the mine. The fuel solved the problem it created. That's the virtuous cycle. It never started in antiquity. There was no coal crisis, no deep flooded mines creating an urgent need for pumps. The primary fuel, wood, was a surface resource. You didn't need to dig a deep, dangerous shaft to get it. So the pressure, the financial incentive to solve a fuel extraction problem, it just wasn't there. The energy economy was stable, sufficient, geographically tethered. It wasn't breaking, demanding a new kind of power. This logistical reality ties into systems of control. A decentralized, biomass-based energy source reinforces a certain social structure. Thermal power is spread out in every village woodlot. It doesn't centralize. It doesn't create the dense, fuel-hungry hubs that become factories. The Roman Empire could command legions, build aqueducts, but its energy infrastructure couldn't support a Manchester. The empire ran on grain, taxes, human labor, not on concentrated fossil energy. So the fuel question isn't just about chemistry. It's about possibility. The available energy sources shaped what was conceivable. They enabled a civilization of artistry and engineering, but they also drew a boundary the spinning bronze sphere could never cross. It was a device waiting for a different world. A world powered by black rock dug from the deep, by a new, relentless hunger for mechanical work. The knowledge to build these things, it was held by different people. In the ancient world, thinking and making were separate. The philosopher, the scholar-like hero, they were from a privileged class. They studied natural philosophy, the principles of the world. And the craftsman, the metalworker who actually made the bronze sphere, he worked with his hands. This was more than a division of labor. It was a hierarchy. Abstract thought was placed above practical skill. A scholar might design a device to demonstrate a principle. An artisan would execute it with incredible craftsmanship. But these two worlds, they rarely came together into one continuous process of solving problems. Technical knowledge was often personal, guarded. It wasn't part of a shared body of work that grew over time. There were no engineering guilds passing down blueprints for steam pumps, each generation improving the design. Knowledge was fragmented. A brilliant insight could be written on a scroll, stored in a library, and then forgotten for centuries. It wasn't out in workshops. It wasn't being tested, broken, and rebuilt by people facing the gritty problems of daily work. This separation had a profound effect. It meant innovation was often top-down, theoretical. It responded to the curiosity or the symbolic needs of the elite, not the practical pressures of production. When the state took on a massive project, an aqueduct, a colosseum, a triumphal arch, the goal was glory, the stability of the state, the favor of the gods. These projects consumed enormous resources and labor, but they were monuments, not factories. They displayed power. They didn't create a new economic system. They solved the problem of moving water for a city, but not with an eye toward mechanizing all other forms of work. There was no emerging class of independent industrialists. No capitalists looking to invest in a risky new machine to spin cotton faster. No patent offices. No culture of the lone inventor tinkerer in a garage, driven by the dream of a marketable product. The social and economic rewards, they simply weren't aligned that way. Why would a wealthy landowner fund a steam engine? To do what? Replace the enslaved workforce that was already maintaining his estate. That would be an investment with no clear return, and it might even disrupt the social order he depended on. So the engine's potential was stifled by the very fabric of that society. A fabric woven with threads of hierarchy, where the control of knowledge and the purpose of technology served to reinforce the status quo, not to overturn it. And this brings us to the final barrier, the most subtle one. It lives not in furnaces or social ranks, but in the human mind itself, a barrier of perception. Aristotle used the term banausic. It was a word of disdain. It pointed to manual arts, to crafts, to work done with the hands. For him, that kind of labor was vulgar. It coarsened the mind, it coarsened the body, a necessary part of the city, but not a noble one. True excellence was elsewhere, in contemplation, in politics, in the life of the mind. And this wasn't just one opinion. It was a cultural current. It created a hierarchy. At the top, the abstract, the political. At the bottom, the practical, the mechanical. So a device like the Aeolipile, where did it fit? Was it a triumph of the mind, or just a clever toy from a metalworker's hands? The answer was often ambiguous. You could admire it as a demonstration, a proof of a natural principle, but to celebrate it as a tool, something to make manual labor easier. That was a much harder idea to accept. That would mean elevating the banausic, using the mind's genius to serve the very thing the mind was supposed to rise above. And that created a disincentive, a subtle one. The brightest thinkers, the ones with education and resources, they were looking elsewhere. Their prestige came from timeless questions. Not from the gritty problems of a mill or a mine, but there was another voice, Vitruvius, the Roman architect and engineer. In his work De Architectura, he celebrated engineering. Engineering in service of the state for public welfare. Aqueducts, siege engines, public buildings, these were noble. They served the community. They displayed the power of Rome, the benevolence of Rome. So that was a different validation. Technology for the public good, for glory, for utility. But the focus is important. It's on grand public works, on military application, on civic infrastructure, not on private devices, not on labor-saving machines for economic gain. An engine for a bakery or a workshop didn't fit neatly. It wasn't pure contemplation, and it wasn't a monumental public work. It sat in a quiet middle ground without a strong ideological patron, and some schools of thought were more direct. The cynics, for instance, they rejected luxury. They rejected complex technology outright. They saw it as a distraction from virtue, a source of softness, of dependency. To them, a machine that eliminated hard work might not be a blessing. It could be a curse, leading to idleness, to moral decay. That fear of technology, that it might corrupt rather than uplift, it's an ancient thread. The myth of Daedalus and Icarus carries that warning. Human ingenuity, overreaching, leads to a fall. So the cultural narrative then wasn't about linear progress. The idea that each generation should improve upon the last through better tools, that the human condition was meant to be endlessly eased by machinery. That simply wasn't the dominant story. Their stories were about cycles, golden ages lost and found, about maintaining balance, about order, about wisdom, not just efficiency. In that environment, an invention like a practical steam engine lacked a supporting ideology. There was no chorus arguing that saving labor was an inherent good. No cultural imperative to mechanize for productivity itself. The philosophical landscape provided little wind for that sail. So with all these layers, the economic, the material, the scientific, and now the philosophical, you can look back at the Aeolipile itself, not as a failure, but as a perfect product of its world. Its design tells a final, quiet story. The Aeolipile spun with this elegant motion. It was a reaction turbine driven by jets of steam, and that kind of design has a basic problem when it's slow. It doesn't create much torque. Torque is that twisting force, the thing that does the actual work. Like when you're trying to loosen a bolt, you push on the wrench. That push is torque, so the Aeolipile's spin was graceful, but it had no strength. It couldn't start if it was already connected to something heavy. If you hooked it to a millstone or a pump, that resistance would just stop it. It was a sprinter that needed a running start, but the world needed a weightlifter. Something that could move a huge load from a complete stop. That's why it worked perfectly as a temple display, spinning in the open air. And why it was useless for the job that started the Industrial Revolution, pumping water out of a flooded mine. Its wastefulness went further. The design was an open cycle. Steam shot out of those nozzles and went right into the air. All that heat energy went with it, and the water was gone too. To keep it going, you had to boil more water constantly. You were throwing away fuel and the working substance every time it turned. A thirsty device. Now look at the engines that changed things over 1,000 years later. Thomas Newcomen's atmospheric engine. It used a piston inside a cylinder. Steam would fill the cylinder, then they'd spray cold water to condense it. That created a vacuum, and atmospheric pressure, the weight of the air itself, would slam the piston down. That was a powerful back and forth stroke, ideal for pulling a pump rod up and down. It was a closed system. The condensed water could be collected, used again. It turned the steam's heat into a strong, linear push. James Watt's improvements later sealed it even more, reusing the steam's heat, making it far more efficient. These were engines of push and pull, not spin. Their motion was directly useful. You could connect it with a simple beam to a pump, or later, with gears, to rotary machines. The Aeolipile's rotation was a dead end for its time. Ancient industry needed two things: grinding grain and lifting heavy weights. A rotary millstone needs constant, powerful torque. A water-lifting device needs a strong, repetitive lift. The spinning sphere offered neither. Its motion was all wrong. Even if someone in Alexandria had looked at it and seen a machine for work, the form itself fought that purpose. The materials couldn't handle high pressure. The design wasted energy. The type of motion was mismatched. It was like inventing the wheel, but making it from soft clay, expecting it to carry a chariot. The desire to use it might have been the first step, but the physical recipe was flawed. It shows something about invention. A brilliant idea can be trapped by its first physical form. Without the right materials, the right mechanics, a clear and practical problem to solve, even the most beautiful idea can just spin in place, a captive of its own elegant design. The Aeolipile needed a purpose, some first job important enough to justify building it. Every technology that changes the world starts with that. For the steam engines that started the industrial age, that job was pumping water out of mines. The mines held coal and tin, the very materials the new machines needed. It was a loop. The problem created the solution, and the solution let you create more of the problem. A killer application. So did the ancient world have a killer app for steam? We can look at the possibilities. First, irrigation. Lifting water to fields is constant work. Could a steam pump have helped? Maybe, but they already had solutions: the shatuff, a lever with a counterweight; the noria, a water wheel turned by the river itself. These were made of wood and stone. They needed no fuel, no metalworkers, no risk of explosion. They were understood, and they were cheap. Why would anyone choose a complex, fire-breathing machine when a wooden wheel did the job for free? The economic reason wasn't there. Then, milling, grinding grain, was the most important mechanical task. The Romans used mills turned by animals or people. They used water mills. Later, they even built mills powered by the tides. The technology was moving, but it was moving along a path of water and muscle. A steam-powered mill would have been a leap into the unknown, for a process they already managed with tools that worked well enough. The gain wasn't compelling. And finally, spectacle. This is where the Aeolipile actually lived, in temples and gardens. Could it have been developed for grander displays, for temple wonders? Possibly, but that market was small. The audience was a few wealthy patrons. The investment was for prestige, not profit. Without a profit motive, without a large market, there's no engine for improvement. You build one marvelous device for a king, and then the project ends. There's no feedback loop from 1,000 factories, each trying to make their pump a little better. Without that loop, the technology stops. The ancient world lacked that severe economic pain point. A problem so bad the only answer was steam. Labor was available. Water and animal power were sufficient for the scale of what they did. The cost of developing a whole new prime mover was too high when the old one still worked. The steam engine was a solution without a problem, a prototype without a market. That absence of demand might be the most practical explanation. It leads to a final, somber turn. The great library of Alexandria, where Hero probably studied, didn't last. The knowledge it held, including the scroll about the spinning sphere, faced a fate that would make the question of a killer app suddenly and tragically irrelevant. The fate of an idea comes down to survival, and for knowledge, survival needs a network, a chain of copies, of translations, of hands that pass it along. The Great Library of Alexandria was one of the first of these networks, a hub where scrolls from everywhere were gathered and copied and studied. It was in that climate, that shared curiosity, where Hero of Alexandria probably worked. His scrolls on pneumatics, on mechanics, on steam and air, they were in that collection, but the library wasn't permanent. Over centuries it faded. A slow decline of funding, fires, the decay of time and politics. The building, the institution, the physical collection, it all diminished, and when that happened, something fragile began. That concentrated network of knowledge started to fray. Hero's ideas, the precise instructions for things like the Aeolipile, they faced a new challenge. They had to travel, and the journey of a book in the ancient world, the medieval world, it was arduous. It was perilous. The texts didn't vanish, though. That's the thing. They migrated. As the Western Roman Empire fell apart, the center of Greek learning shifted east to the Byzantine Empire. Scribes in Constantinople, the New Rome, they copied Greek manuscripts onto parchment. They preserved Hero's pneumatica, but the context changed. In that Byzantine world, these works were studied for philosophy, for mathematics, as part of a classical heritage to admire. The practical, mechanical wonders were sometimes viewed with suspicion, as potential conduits for magic or pagan thought. The knowledge was saved, but it was placed behind a kind of glass case. It was an artifact to be commented on, not a blueprint to be built from. Then another hand reached for these texts. As Islamic civilization expanded, it actively sought out Greek scientific works. In Baghdad's House of Wisdom, scholars translated Hero into Arabic. They studied him deeply. The great polymath Al-Jazari, in the 13th century, wrote his own book of knowledge of ingenious mechanical devices. It's filled with automata, water clocks, wine servers, musical robots. You can see Hero's influence there, but the focus is telling. these are devices of courtly wonder, of hydraulic elegance for palaces. They are masterpieces of craftsmanship and entertainment. Not one of them is an engine designed to pump water from a mine or to drive a loom for cloth. The knowledge was preserved, even expanded in its artistry, but its potential for industrial transformation stayed dormant. The Pneumatica was a book of marvels, a testament to cleverness. It was never treated as an engineering manual for builders, something to take out to a workshop and iterate on. The reason is in the medium itself. Before the printing press, every book was a singular treasure. A manuscript copied by hand on expensive parchment. The process was slow, costly, prone to errors with each new copy. This meant knowledge was rare. It was heavy, literally. A library was a fortress of wealth. Books were chained to desks. This physical scarcity created isolation. A monk in Italy might have a text on mechanics. A scholar in Cairo might have another, but they would almost never compare notes, debate a design flaw, share a breakthrough in metallurgy that could make Hero's sphere stronger. There were no scientific societies, no journals, no conferences, no patent offices where an inventor could publish a design for others to see and improve. An idea could be rediscovered like an artifact dug up from the past, but it couldn't become part of a living, growing tradition. It was a footnote, a curiosity in a margin. The Aeolipile pops up in manuscripts for centuries after Hero, a medieval drawing here, a passing mention there, but each time it's presented as that same wonder. A spinning ball that demonstrates steam. The commentary doesn't ask how to connect it to a mill. It marvels at the ingenuity of the ancients. The knowledge was static, trapped. This break in continuity is devastating for progress. It means every generation essentially starts from scratch or from a very incomplete set of instructions. The cumulative, collaborative nature of modern engineering, where one failure informs another's success, it simply couldn't exist. The ecosystem was missing. An ecosystem of cheap, widespread communication, of shared standards, of a community that valued incremental, practical improvement over singular marvels. So when we ask why the ancient steam engine failed to launch a revolution, part of the answer is simple. The instructions for it and the conversation about how to make it better, they couldn't get to the right people. They couldn't travel fast enough or far enough or into the right hands. The knowledge was preserved, but it was never truly alive. It was waiting for a world that could not only read the words but hear the call to action in them. A world that would eventually emerge from a different kind of pressure, not from philosophical curiosity, but from a very tangible, very urgent need deep underground. Centuries later, on another island, the pieces finally came together. 18th century Britain was this perfect storm, a unique environment where the seed of steam could actually take root and grow. To see why Hero's device stayed a wonder, you look at what Britain had that Alexandria didn't. First, the fuel. Britain had huge coal seams, easy to reach, often near the surface or close to water. This wasn't just a curiosity, it was a national resource. But as they dug deeper for it, the mines flooded. That created a desperate problem and an expensive one. The demand for a solution wasn't philosophical, it was financial, a direct economic pressure, a reward for anyone who could build a machine to pump the water out. So the fuel source created the very problem that demanded its use. Second, the material. British ironworking had advanced. They'd mastered making high-quality cast iron in blast furnaces. This strong, cheap metal could be cast into big cylinders and pistons, and the precision tools were there, like John Wilkinson's boring mill, which could drill a near-perfect cylinder. That gave engineers the physical parts to contain high-pressure steam safely. Third, the legal and social side. Britain had a patent system, flawed, but it offered inventors like James Watt a temporary monopoly, a chance to profit from an improvement. That incentivized tinkering and investment. There was also the Royal Society, a growing community, a place where natural philosophers and practical mechanics could exchange ideas. Science was becoming less about pure thought, more about useful knowledge. Fourth, the economic signals. Wages in Britain were rising. Labor was getting more expensive relative to capital. That made investing in labor-saving machinery a smart calculation for factory owners, for mine operators. And there was a growing capitalist market, hungry for cheaper textiles and metal goods. That created a pull, a demand for more efficient production. Fifth, the culture, a culture of practical tinkering. Men like Thomas Newcomen weren't university scholars. They were ironmongers, instrument makers, hands-on problem solvers. They worked in workshops, not libraries. Their genius was applied, iterative. They would build an engine, watch it fail, and then figure out why. Make it a little better each time. Now hold that picture next to the ancient world. Alexandria had brilliant scholars, but no flooded coal mines screaming for a pump. It had skilled bronze workers, but not an industry of cheap, strong cast iron. It had wealthy patrons, but no patent system protecting an inventor's right to profit. Its economy was built on abundant human labor, not rising wages that made machines attractive. Its thinkers were often separated from its makers by a deep social divide. The steam engine that changed the world wasn't a single invention. It was the apex of a vast, invisible pyramid. That pyramid was made of coal seams and iron foundries, patent law and market demand, a culture of improvement and a network of shared knowledge. Hero's Aeolipile was a sparkling crystal placed on empty sand. The British engine was that same crystal, but now resting on top of a mountain of enabling conditions that took centuries to build. This comparison clarifies everything. The ancient attempt wasn't a failure of intelligence. It was a matter of context. The idea was breathtakingly premature. It arrived in a world that could admire its beauty but couldn't possibly use its strength. The necessary ecosystem just wasn't there. With that stark contrast in mind, you can finally ask the question that's hovered over this story from the start. What if that context had been different? What if they had? What if the Romans had actually built a working steam engine? Not just a temple toy, but something practical. You'd hear it first in the city, down in the basements of those tall apartment blocks. A steady thumping, a steam pump, lifting water up to the higher floors. A city that needed 1 million gallons a day, no longer just relying on aqueducts ending at street level. Now water could climb, buildings could climb too. The shape of the city might change, then the construction sites. The Colosseum took 10 years to build, human and animal power, but a steam-powered crane. A treadwheel driven by a fire instead of men walking in a circle. How fast could you lift those stone blocks then? Temples, baths, forums, the architecture of an empire built with steam, and the military. The legions were masters of supply, but they moved at the speed of ox carts and sailing ships. Now imagine a narrow wooden railway, iron-clad wheels, a small locomotive chuffing along. Not for people, for grain, for armor and artillery parts from a port to a frontier fort. Roman power could reach farther, faster on land. Reinforcements and supplies arriving with a reliability no other army could match. The psychology of the frontier would shift under that weight. That mechanical certainty, but then it gets darker, more interesting, because technology never arrives alone. It creates waves, destructive waves. The first shock would be social. The Roman economy rested on human labor, free and enslaved. What happens when steam-powered mills grind grain without millers, when cranes lift without laborers? When pumps work without water carriers, sudden, massive displacement, unemployment on a scale the grain dole could never handle. The result wouldn't be leisure. It would be desperation, riots, a crisis of purpose for a huge part of the population. The Pax Romana was fragile. This kind of shock could shatter it from within. Then the environment. Roman forges already stripped forests for charcoal. A steam-powered industry would need so much more fuel. They had coal, but in limited deposits. They'd strip those seams bare in decades. The clear skies over the city gone, choked with soot and smoke. The Tiber running warm with waste heat. The villas in the hills looking down on a darkened, coughing Rome. And that hunger for resources would drive the empire to expand even more aggressively, not just for slaves and silver, but for coal mines and forests. More conflict, more overextension, so you get two visions. One, a Rome of impossible grandeur, its might amplified by machines. The other, a Rome torn apart by the very engine of its progress. Collapsing under social and ecological pressures it couldn't manage. Both are plausible, and that's the point. The steam engine was never just a machine. It was a key, and when you turn a key, you don't unlock just one door. You unlock a labyrinth. Economic consequences, social consequences, environmental consequences. The Romans built aqueducts, but they didn't have an economics for technological unemployment. They had laws, but not environmental protections. They conquered resources with no idea of sustainable extraction. The lesson is that an invention alone is never enough. A society has to be ready to absorb the shockwaves, ready technically but also institutionally. Economically, philosophically, the steam engine didn't fail in antiquity because the Romans weren't smart enough. It failed because their world wasn't resilient enough. It wasn't wired for that kind of change, and that realization echoes far beyond the ancient world. The pattern is haunting. The steam turbine idea started in Alexandria, and it just wouldn't stay buried. It kept coming back, a ghost of a revolution that could have happened. Then in the 16th century, inside the Ottoman Empire, there was this brilliant polymath, Taqi al-Din. He wrote a book called The Sublime Methods of Spiritual Machines, and in it he described a device, a way to rotate a spit. It used steam, a jet from a boiling pot, directed onto the vanes of a wheel, making it spin. It was a practical application in theory, a steam-powered rotisserie, but like Hero's sphere, it stayed a description in a book, a wonder for the court. Ottoman society at the time was advanced, sophisticated in many sciences, but the same barriers were there. No pressing economic crisis demanded this machine. No industry of precision metal casting was ready to build it at scale. It was again a solution without a compelling problem. Then you jump forward another century to Italy in 1629. An engineer named Giovanni Branca published a book of machines. One engraving shows a steam turbine. A jet of steam blows right onto the paddles of a horizontal wheel, which is connected by gears to a pair of pestles. For pounding material in a mortar, Branca called it an engine for raising water or pounding powders, and here, at last, was a clear link to mechanical work. But again, it was just a drawing, a concept. There's no evidence it was ever built to do real labor. The Renaissance was a time of rediscovering ancient knowledge, including Hero's works. Artists and engineers sketched fantastic machines, dreaming of power, but turning those sketches into reliable, day-in, day-out engines required an infrastructure that didn't exist. The metallurgy wasn't consistent enough. The scientific understanding of pressure and efficiency was still nascent. The market for factory power was still a whisper. So why did these later rediscoveries also lead nowhere? They reinforce the lesson with brutal clarity. A single brilliant mind, or even a handful of them, is not enough. You can have the blueprint, you can even have a clearer vision of its use than Hero did. But if the surrounding ecosystem isn't ready, the idea stays trapped on the page. The 16th and 17th centuries were building that ecosystem brick by brick. The printing press was spreading ideas faster. Experimental science, through figures like Galileo, was beginning to ask how the world worked in measurable terms. Global trade was creating new wealth and demand, but the key pieces were still not fully assembled. The deep coal mines and their flooding problems were primarily in Britain, not the Mediterranean. The culture of iterative, profit-driven engineering was still coalescing. These historical echoes aren't failures, they're signals. They show the idea of steam power wasn't a fluke, not a one-time spark of genius. It was a logical, reachable conclusion that multiple advanced societies stumbled upon independently. It was an idea whose time had almost come, again and again. But almost is the entire distance between a curiosity and a world changer. The Aeolipile and its descendants were seeds of incredible potential, but for over 1,500 years they kept landing on pavement or in shallow soil. They'd sprout a little green shoot of recognition, a drawing in a book, a description in a treatise, and then stall. They were waiting for the deep, fertile, messy soil of a very specific time and place. A place where coal was king, where iron was cheap, where mines were drowning, and where a culture believed in progress through machinery. That wait, though, wasn't the end of the story. The ghost of the spinning sphere had one last, surprising role to play, not in ushering in the industrial age, but in shaping how we understand it. That spinning sphere found its purpose later. Not in a factory, in a classroom. You can go into a science museum now, almost anywhere, and you'll see a model of the Aeolipile, usually a bronze replica. Sitting over a small flame, turning slowly behind glass. It's not a temple wonder anymore. It's an educational icon, a clean demonstration of a basic law. Newton's third law, action, reaction. The steam goes out one way, the sphere spins the other. It's the same principle that runs jet engines, rocket propulsion. In that simple spin, students see the seed of the technology that got us to the moon. The device that didn't start an industrial revolution starts 1,000 moments of understanding instead. And its legacy is hands-on. Online, there are tutorials, how to build your own from a soda can, some copper tube, a tea light. School kids and hobbyists make heroes' invention on kitchen tables. They watch heat turn into motion right there. In this form, the engine works perfectly. It's accessible, clear, it teaches physics and it teaches history. It connects a student now to a thinker in the 1st century. A direct thread of curiosity across 2,000 years. So what is it now? It's a symbol of ancient ingenuity, sure. A testament to a mind that saw a possibility no one could use yet. But it's also a cautionary tale, one we teach without saying it. It sits in the museum case as a quiet lesson about innovation itself. It shows that progress isn't a straight line from idea to application. It's a messy journey. It depends on an ecosystem, the right materials, the right economic pressures, the right cultural mindset, a network of knowledge to sustain an idea across generations. The Aeolipile had the spark, but it landed in a world without the kindling. That reframes the idea of success. For centuries, we looked back and saw a dead end, a what if, but from another angle. Its journey isn't a failure. It started as a philosophical demonstration. And after a long trip through history, through libraries and rediscoveries, it ended up fulfilling that original purpose. Even better, it demonstrates a principle. It inspires wonder, it educates, it found its perfect niche, not as a prime mover of industry, as a prime mover of the mind. Its circle is complete. From the temples of Alexandria to today's classrooms, it spins on. A reminder that sometimes an invention's most enduring success isn't the work it does. It's the questions it keeps asking. Success is a story we tell ourselves. It's something we decide later, and the story we tell about the Aeolipile, that's a modern story. We see that spinning sphere, and we think that's a machine that didn't change the world. We compare it to the factories of the 19th century, the trains. By that measure, it was a failure. A spectacular one, but that's like judging a medieval clockmaker for not inventing the smartphone. You're using a definition of success that wouldn't exist for another 1,700 years. By the standards of its own time, the Aeolipile was a stunning achievement. You have to remember its audience, the philosophers, the patrons, the people at the temple. Their goal wasn't economic output, it was understanding, it was wonder. The display of human ingenuity aligned with natural law. In that arena, the device was a champion. It took an abstract principle, the reactive force of steam, and made it visible. Made it tangible, mesmerizing. It answered a philosophical question with elegant motion. It cemented Hero's reputation as a master of mechanics, a man who could make the secrets of the air dance before your eyes. In a culture that valued demonstration, that valued spectacle as a high form of knowledge, this wasn't a failure, it was a masterpiece. Different societies asked different things of their technology. For the Romans, technology served the state, it served the gods, the display of power. Aqueducts brought civic order, triumphal arches projected imperial glory. The Aeolipile, in its own way, served a purpose just as vital. It fed the intellect, it was a tool for education, for philosophical debate. Its success was measured in the awe it inspired. The conversations it sparked, the scrolls it filled, not in the tons of coal it could move. Our modern obsession, this linear, utilitarian progress, it can blind us to that. We see history as a race toward efficiency, a march of increasing control over nature, and when an invention doesn't propel that march forward, we label it a dead end. A curiosity, but that says more about our own values than about the device. It reveals our deep-seated belief that the ultimate purpose of technology is to produce. To automate, to dominate. The ancient world had a different palette of purposes: to explain, to honor, to delight, to contemplate. So the Aeolipile's so-called failure to launch an industrial revolution, that isn't a flaw in the device. It's a mismatch between its cultural mission and our historical hindsight. Its journey asks us to step outside our own frame, to appreciate ancient technology on its own terms. To see a water clock not as a primitive timer, but as a symphony of hydraulics and artistry. To see the Antikythera mechanism not as a computer that didn't lead to laptops, but as a breathtaking model of the cosmos crafted in bronze. This reframing isn't about dismissing the lessons of history. It's about enriching them. We can hold two truths at once. We can admire the Aeolipile as a brilliant success within its world, while also understanding the complex web of reasons why its potential lay dormant for centuries. This dual perspective is powerful. It frees us from a narrow, judgmental view of the past, and it prepares us to ask the most practical question. If this story isn't about a single failure, but about the ecosystem required for transformation, what concrete lessons can we take from it? What does this 2,000-year detour teach us about how innovation really works? The spinning sphere gives us a clear picture of how progress works. A breakthrough invention is never really alone. It's just the most visible piece of a much larger system. And if any part of that system is missing, the invention can't take hold. With the Aeolipile, we can point to each missing piece. The science piece, a deep, mathematical understanding of heat and motion. The technical piece, materials like refined iron, precision tools. The economic piece, a desperate, profitable need, like flooded mines that needed pumping. The cultural piece, a society that valued machines for work, not just for wonder. And the resource piece, an abundant, concentrated fuel like coal. The ancient Hellenistic world had remarkable parts of the first two. Brilliant science, incredible craftsmanship, but the other three weren't there. There was no connected web. The economic signal wasn't loud. The cultural story wasn't about saving labor. The fuel logistics didn't work, so the invention stayed isolated. A single, shining point in a network that wasn't built yet. Then you look at 18th century Britain. There, all the points suddenly connected. The scientific questions from the Royal Society met the technical skill of ironworkers. The economic desperation of mine owners met a culture of tinkering and patents. And underneath it all, the abundant resource of coal fed the entire cycle. Each part strengthened the others. Better pumps meant more coal meant more iron for better engines, which drew more investment and smarter engineers. That's an innovation ecosystem actually moving. It's not a straight line from a bright idea to a changed world. It's a messy, living network. This matters now. Take any field ready to change, artificial intelligence. The core idea of neural networks is old. Why is it exploding now? Because the ecosystem finally lined up. The scientific theories matured. The technical capability arrived with powerful chips and huge datasets. Economic demand surged from every industry wanting automation. Cultural acceptance grew as the tools entered everyday life, and the resource data processing power became everywhere. The idea from the 1950s needed the 21st century's ecosystem to become real. You see the same pattern in biotechnology, in renewable energy. A brilliant lab discovery about solar cells means nothing if you can't make them cheaply, if there's no grid to support them, if policy and public will aren't there. The myth of the garage inventor is powerful, but it's incomplete. The individual spark is essential, but that spark needs the right air to become a flame and the right forest to sustain a fire. The Aeolipile shows that a society can be amazingly advanced in one way, yet completely unready for its own cleverest creations. That shifts our focus from worshipping the lone genius to understanding the fertile ground. It makes us ask not just what's being invented, but what world is being built around it. And that leads straight to the oldest saying in the book, one the Aeolipile story twists in an interesting way. The idea that necessity is the mother of invention. That saying about necessity only gets it half right. Necessity can push things forward, but the Aeolipile makes you wonder, what if the need is there but the invention never comes? The ancient world had huge needs, lifting water to dry fields, moving heavy stone for monuments, grinding grain faster for growing cities. These weren't small issues. They were central to keeping civilization going, and still the steam engine didn't appear to solve them. The reason was that specific, urgent, profitable need for a steam engine just wasn't there. The solutions they already had: human labor, water wheels. They seemed good enough. The cost of developing a whole new kind of engine was seen as higher than the cost of just sticking with the old ways. So necessity alone wasn't enough. It had to be a particular kind of necessity, one that the old tools couldn't handle, and one that had enough economic force behind it to make the huge risk worthwhile. The flooded coal mines in 18th century Britain created exactly that. It was a crisis that broke the old models, made the steep price of innovation worth paying. In Alexandria, the need was broad and general. In Cornwall, it was sharp, specific, and financially desperate. That shows the saying's limit. Necessity might be a mother, but she's a selective one. She only gives birth when the conditions are exactly right. But then there's the other side. Sometimes invention is the mother of necessity. A new technology, once it works, creates demands that never existed. Before the practical steam engine, who desperately needed a locomotive, before the smartphone, who felt a burning need to carry the internet in their pocket. These technologies didn't just answer old calls, they created new ones. They reshaped what we even desire. They made us need things we never knew we wanted. The Aeolipile couldn't do that because it never reached that point of being viable. It was an invention that couldn't yet show a clear advantage. It couldn't create its own necessity because it wasn't yet necessary for anything. It lacked that first foothold, and that points to a different kind of person. Not just the problem solver, but the visionary. The tinkerer who builds something not because the world is shouting for it, but because they see a glimmer of another possibility. James Watt didn't just make a better pump. He saw the potential for a new source of rotary power that could change manufacturing. His vision helped create the very necessity his engine would later fill. So the story of steam is a kind of dance between a sharp crisis and a broad vision. It shows that waiting for a glaring, obvious necessity might mean waiting forever. The real leaps often come from people who combine a deep grasp of a problem with the foresight to build a tool that redefines the problem itself. They don't just meet a demand. They manufacture it, and by doing that, they change what a society thinks is possible and what it believes it needs to survive. Hero of Alexandria wasn't responding to a market. He wasn't trying to meet a quota, he was just playing. He had this simple urge: what happens if? That question, asked out of pure curiosity, led him to steam. To spinning metal. His workshop was a playground for pneumatics, a place where you could combine air and water and fire just to see what happened. The Aeolipile wasn't a grim tool. It was a joyous experiment, a celebration of a principle made visible, and in that there's a lesson one modern societies focused on quarterly results can forget. The lesson of tinkering, the value of curiosity-driven exploration, research for the sheer wonder of it. We often think of progress as linear. A problem appears and clever minds engineer a solution. But history shows a messier path. Breakthroughs often come from the side, from people following a fascinating thread with no clear end in sight. The laser started as a solution looking for a problem. A physicist's elegant proof about light. Penicillin began with a moldy Petri dish a curious researcher decided not to throw away. The foundations of the internet were laid by researchers sharing data between universities. Not by entrepreneurs planning a marketplace. These were acts of basic research, playful investigation. Their practical power was a secondary effect, sometimes realized decades later. Hero's spinning sphere fits this pattern. It was basic research in bronze. He was exploring the properties of heated air and steam. His goal was understanding, not utility. He was planting a seed in shallow soil, a seed that lay dormant for 17 centuries. But when the ecosystem changed, when economic and material conditions aligned, that seed was there. The intellectual seed, the idea that steam could create motion. It provided a starting point, a reference, a historical whisper that said, this is possible. Newcomen and Watt didn't start from a blank slate. They stood on a foundation built by centuries of thinkers and tinkerers, many of whom, like Hero, were just playing with the forces of nature. This reframes what we mean by useful. A technology that doesn't find an application for 1,000 years, is it useless? By the narrow standards of quarterly profit, maybe. But on the grand scale of human knowledge, it's a vital data point, a proof of concept. It expands the realm of the possible. It tells future generations someone already thought of this. The path exists. The value of Hero's work wasn't in the work it did. It was in the idea it preserved, the door it left unlocked. Our modern world is built on a vast accumulation of such unlocked doors. Discoveries made by people simply following their curiosity, mapping the territory of the unknown without knowing what would be built there later. We see this spirit today. In large particle colliders searching for fundamental bits of matter with no immediate engineering purpose. In robotic labs where engineers build machines that mimic animal movement, just to understand the principles of agility. In open-source software communities where people build tools for the joy of solving a puzzle. These endeavors may seem disconnected from daily life, but they are the modern equivalent of Hero's workshop. They are the playgrounds where the foundational concepts of tomorrow are being discovered, often by accident. The playful tinkering of today is the basic research that becomes the indispensable tool of the 22nd century. To only fund research with a guaranteed short-term application is to starve this process. It's to cut the root and expect the tree to keep bearing fruit. The Aeolipile, then, is more than a footnote about a failed engine. It's a monument to a state of mind, a mind free to explore, to ask what if, to build a spinning metal sphere just to watch it go. That spirit of inquiry for its own sake is not a luxury. It's the engine of the very long game, the game that spans civilizations. It reminds us that before a technology can change the world, someone first has to dream it into being. For no other reason than the pure, exhilarating joy of the dream itself. Hero's spinning sphere has a direct descendant today. It's in a laboratory now, not a temple. It's called the experimental fusion reactor. For decades, scientists have been trying to harness the power of the stars here on Earth. They built these massive machines, tokamaks, using powerful magnets to hold a superheated plasma. They've achieved fusion for brief moments. They've shown the principle works just like Hero did. The reaction happens. The potential is almost unimaginable, a near limitless source of clean energy. But it's still largely a demonstration, a brilliant proof of concept trapped by practical challenges. The materials that can withstand that heat, that neutron bombardment for years on end, they don't fully exist yet. Net energy gain, getting more out than you put in, that's only been reached recently and in fleeting experiments. The economic model for building plants complex enough to power cities, that's still just a sketch. Fusion energy is our modern Aeolipile, a wonder waiting for its ecosystem. You see the same pattern with quantum computing. The core idea is revolutionary. Instead of binary bits 0 or 1, you have qubits. They can be both at once. This could let them solve certain problems in medicine, materials, cryptography problems that would take conventional computers millennia. Labs have built small quantum processors. They've run algorithms that prove the principle, but these machines are extraordinarily fragile. They need temperatures colder than deep space. They're prone to errors. The software to program them for broad applications, it's in its infancy. Right now, they're spectacular research tools. They solve puzzles we set for them to show their potential. They're not yet the general-purpose engines that will redefine industries. They exist in a state of promise, constrained by cryogenics, by error correction, by a lack of killer applications outside very specialized fields. They are demonstrations of a new logic, waiting for the supporting technologies to catch up. Even in artificial intelligence, you see echoes. Branches like artificial general intelligence, the pursuit of a machine that can understand and learn any task a human can, they exist in this realm. Researchers have built narrow systems that excel at specific games or generate coherent text. These are demonstrations of capability. They hint at a broader future. But the path from a language model that writes a poem to a system with genuine reasoning, with common sense, with adaptable understanding, that's a chasm. It's constrained not just by algorithms and computing power, but by our fundamental understanding of consciousness itself. The goal is clear. The principle is being explored in fragments. But the complete, usable, safely integrated technology that remains on the far side of breakthroughs we can't yet schedule. These modern parallels make the ancient story vibrate. They remind us the timeline for a transformative technology isn't measured in product cycles. Sometimes it's measured in generations. The gap between a dazzling prototype and a technology that quietly powers everyday life, that gap can be vast. It's filled with unglamorous problems, engineering problems, infrastructure, economics, a society that only celebrates the initial breakthrough and loses patience before solving the mundane follow-up challenges. That society may never reap the reward. The Aeolipile teaches us to look past the headline-grabbing demo, to ask the harder questions. Do we have the materials to make this robust? Is there a clear, pressing need that makes the development cost worthwhile? Is the cultural and economic system aligned to support its integration? Or will it disrupt too much, too fast, and create resistance? That spinning sphere from Alexandria forces us to examine our own technological frontier with a historian's eyes, not to doubt the potential, but to map the entire journey required to realize it. This perspective shifts the conversation from mere invention to responsible cultivation. It asks what kind of world we are building, not just what brilliant device we are dreaming of. And that leads us away from the machines, back to the people who dream them up. The question isn't really about genius, it's about the soil. Hero of Alexandria, he was a towering intellect. A creative force, he could see connections other people missed, but his mind grew in a specific garden, tended by the philosophies, the resources, the questions of first-century Alexandria. He couldn't conceive of a world powered by coal. That world didn't exist yet to conceive. His genius was brilliant, but it was bounded, directed by the curiosities his culture valued. That challenges a comfortable story, the story of the lone great man, the singular intellect bending history. James Watt fits that mold so neatly, the inventor in his workshop, struck by inspiration watching a kettle boil, single-handedly ushering in the modern age. But that story, while romantic, misses the immense scaffolding that held him up. Watt was a genius, yes, but his genius was activated by a context built over centuries. He inherited Newton's laws of motion. He used iron from Wilkinson's precision boring mill. He solved a problem, the inefficiency of the Newcomen engine, that only existed because of decades of prior tinkering in British coal fields. And he operated within a patent system. That system let him partner with the businessman Matthew Boulton, which secured the funding, the manufacturing might, to turn his improved design into reality. If you could transplant a mind like James Watt's into ancient Rome, what would happen? He'd likely have become another hero, a brilliant creator of temple wonders. Philosophical toys, his improvements would have been about spectacle, not efficiency, because the economic pressure to be efficient in that way, the material means to achieve it, the entire network of need and knowledge, it wasn't there for him to plug into. His genius would have been a seed falling on marble. This isn't to diminish individual brilliance, it's to properly credit it. Genius is the spark, but history is largely about the conditions. Whether that spark catches, smolders unnoticed, or winks out immediately, it's about the kindling, the airflow, the forest around it, which brings in the role of chance. Unsettling, thrilling, the story of technology isn't a predetermined march from primitive to advanced. It's a messy, branching path, a labyrinth. At every turn, small contingencies mattered. What if the library at Alexandria had survived intact for another 500 years, its knowledge flowing uninterrupted? What if a particular Roman engineer tasked with draining a swamp had been a relentless tinkerer who saw potential in heroes' designs? What if a different alloy had been discovered, one that could better contain pressure? These are the what-ifs that haunt the edges of history. They remind us our present isn't the only possible outcome. It's simply the one that happened. Built on a long chain of accidents, survivals, missed opportunities, artists and writers have long been fascinated by this. Steampunk, for instance, it's a playground of contingency. Imagining a Victorian age where steam technology advanced along a different, more ornate path, where brass and gears power impossibly complex airships and analytical engines. It's a celebration of an alternative past, a road not taken. These artistic visions are more than entertainment. They're thought experiments. They ask us to loosen our grip on the idea of inevitable progress. To see history as a story with many possible plots, where a single different choice, a preserved manuscript, a curious mind in the right place at the wrong time, could have sent everything spiraling in another direction. The Aeolipile is a monument to one of those alternative paths, a path that glimmered for a moment in a temple, then faded into the scrolls. Its quiet fate whispers that our world wasn't foreordained. It was built piece by contingent piece, and it could have been built very differently. The Aeolipile lived on in books and art. Long after its practical use faded, artists and storytellers brought it back. You find it in the notebooks of Renaissance engineers like Leonardo da Vinci, sketched there among flying machines and war engines. For them, rediscovering old texts, the sphere was a symbol of recovered knowledge. A challenge from the past. They weren't building it to pump water. They drew it to make a point that the ancients had seen mechanical truths they were now exploring again. It was a badge of intellectual heritage. This cultural repurposing sped up with the steam age itself. Once steam power actually changed the world in the 1800s, people looked back. They saw Hero's device differently. It became a convenient origin story, a fitting ancestor for the roaring engines of their time. Paintings and engravings started to show it, often idealized. A gleaming bronze orb on a stand, steam jetting out, symbolizing the dawn of mechanical thought. It was history retouched, made to fit a story of inevitable progress. Then came the 20th and 21st centuries, and the sphere really escaped into myth. This is where it thrives now. In steampunk, the Aeolipile is everywhere. It's reimagined not as a toy, but as the secret heart of impossible machines, the power source for a Roman airship, the core of a Byzantine computational engine. In video games and novels, it fuels an alternate antiquity, where the Industrial Revolution happened 2,000 years early. These stories are knowingly ahistorical. They're fantasies, but they speak to a deep cultural itch. The fascination with lost advanced technology, with the road not taken. They ask, what if that spinning sphere had been the start of everything? What kind of world would we have now? It's a playground for the imagination, built on a single, elegant historical fact. These depictions, for all their inaccuracy, do something vital. They keep the story alive in the popular mind. They turn a museum piece into a metaphor for premature genius, for the glimpse of a future that could have been. When a game designer uses the Aeolipile to power a puzzle in an ancient tomb, they aren't teaching engineering history. They're evoking a feeling, a sense of wonder at a past that feels more knowing, more mysterious than the history books allow. This is how historical fact becomes legend, not through error but through emphasis, through the layers of meaning we choose to add. This cultural afterlife is, in its own way, a profound form of success. The Aeolipile failed to launch an industrial revolution, but it launched 1,000 stories. It secured a permanent place in our collective imagination. Its power as an idea, as a symbol of human ingenuity and historical chance, has proven far more durable than any mechanical force it could ever produce. It reminds us that the legacy of technology isn't measured only in work done or wealth generated. It's also measured in the dreams it inspires long after its fires have cooled. This journey from temple to textbook to video game screen brings us to a final thought. What, when all the layers are peeled back, is the core truth of this 2,000-year detour? The ancient steam engine didn't fail for one simple reason. It was more like a perfect storm of absence, a series of conditions that all had to be in place for that idea to catch fire. And in antiquity, not one of them was fully there. On the technical side, the device itself was a marvel of demonstration, but it was a prisoner of its design. The materials couldn't handle high pressure. Its form produced elegant spin, not the strong, linear force you need for real work. It was a sprinter built from bronze when what the world needed was an iron weightlifter. Economically, the signal was never sent. Labor was abundant. Widespread systems of enslavement made labor a predictable cost. There was no severe financial pain point. Nothing like the flooded coal mines of 18th century Britain. Nothing to make the massive risk and investment in a steam pump worthwhile. Why gamble on a complex, fuel-hungry machine when the existing workforce got the job done? Culturally and philosophically, the purpose of technology was directed elsewhere. Ingenuity went into public monuments, military engineering, philosophical wonders. The Aeolipile was a automata, a marvel to provoke awe and discussion about nature's laws. The idea of mechanizing labor to increase productivity for its own sake, to elevate the practical arts, that simply wasn't a dominant cultural driver. The brightest minds were often looking up at the stars, not down at the problems of the mill or the mine. Scientifically, the framework was incomplete. They grasped the mechanics of levers and pulleys with stunning clarity, but the systematic study of heat, pressure, energy conversion, thermodynamics, that was a chapter not yet written. They could observe that steam made the sphere spin, but they lacked the concepts to measure its efficiency, to calculate how to maximize its work, to see it as a convertible source of power. And underpinning it all were the resources. The ancient energy economy was based on biomass, wood and charcoal, a diffuse, geographically tethered source. It couldn't concentrate the immense portable power needed to feed an industrial system. They lacked the abundant, dense fuel like coal that could both create a demand for steam pumps and then fuel them in a self-reinforcing cycle. Individually, each of these factors was a significant barrier. Together, they formed an impenetrable wall. The Hellenistic world had dazzling islands of capability, in thought, in craftsmanship, in isolated invention. But these islands were not connected by the bridges of a supporting ecosystem. Now contrast this with the perfect storm that brewed in Britain centuries later. Every missing piece found its counterpart. The technical challenge of flooded mines met the material breakthrough of precision cast iron. The economic desperation of mine owners met a culture of practical tinkering and patent protection. The scientific curiosity of the Royal Society met the hands-on genius of instrument makers. And beneath it all, the abundant resource of coal both created the crisis and powered the solution. Each element reinforced the others, creating a feedback loop of innovation that was simply impossible in the ancient context. So the failure of the ancient steam engine wasn't a historical accident. It wasn't a mark of lesser minds. It was the inevitable outcome of a world that, for all its sophistication, was wired differently. Its priorities, its resources, its very structure were not configured to receive and amplify that particular signal. The idea was a broadcast sent on a frequency the ancient world couldn't hear. It would take a profound reshaping of society itself, its economy, its science, its relationship to energy and labor to finally tune in. That silent sphere spinning in its temple 2,000 years ago, it holds up a mirror to our own age. It asks us to reconsider what we mean by progress. We tell the story of technology as a straight line, a steady climb, a march of inevitable improvement, but the Aeolipile shatters that illusion. Its journey shows that progress isn't a law of nature. It's fragile, contingent, a temporary alignment of ideas, resources, economics, and culture. They all have to shine together at the right moment, and when that alignment breaks, even the most brilliant idea can drift. For centuries, a satellite without an orbit, this challenges any sense of historical superiority. It forces a profound humility. The engineers of Alexandria weren't less intelligent than those of Birmingham. They were solving different puzzles, guided by a different compass. Their legacy is a different sophistication, one of philosophical demonstration, public spectacle. To dismiss them as primitive because they didn't build factories is to miss the point. They built wonders that answered the questions their world was asking. Our world asks different questions, and we've built different machines in response. This perspective is a corrective. It asks us to look at our own technological landscape with a critical eye. A wary eye. What dazzling prototypes do we have today spinning in our own modern temples, our research labs, our tech showcases? What might seem like a curiosity to a future civilization? What potential are we overlooking because our economic signals aren't tuned to it, or our cultural stories don't value it? Maybe it's a new form of energy trapped by political hurdles. Material hurdles, or a medical breakthrough waiting for a delivery system the market hasn't figured out. The lesson of the Aeolipile is to look for those disconnects. To ask not just what's being invented, but whether the world around it is ready to receive it. Are we building the ecosystem, the educational foundations? The material supply chains, the economic incentives, the cultural narratives, are we building what will allow the best of our ideas to take root and grow? Or are we, like the patrons of ancient Alexandria, just admiring the spectacle without building the roads that would let it travel? This story is a call for stewardship. Progress isn't automatic, it's not guaranteed by the passage of time. It's a garden we must tend. We have to nurture the soil of basic research, even when it lacks immediate application. We have to pay attention to the mundane enablers, the materials science, the precision manufacturing, the things that turn dreams into durable tools. And we have to remain humble, knowing that our current path, for all its power, is just one path through the labyrinth of possibility. The quiet fate of that ancient steam engine is a gift. It's a reminder that our technological destiny isn't pre-written. It's a story we're writing every day with the choices we make about what to value, what to fund. What kind of future we're willing to build. The sphere has stopped spinning, but the questions it raises are just beginning to turn. That silent sphere. Spinning in its temple 2,000 years ago, it wasn't a failure, it was a beacon, a signal from a different kind of mind, from a different kind of world. And we followed its light, from the sunlit courtyards of Alexandria to the soot-choked mines of Cornwall, tracing the web of reasons why this brilliant invention stayed a might-have-been. Its quiet fate shows something fundamental. Technology never exists in a vacuum. It's born from the society that creates it, and bound by it, culture, economics, resources, human imagination. These are the invisible forces. They decide whether an idea becomes a tool or stays a toy. This journey through time asks us to look at our own technological landscape. To see it with new eyes. We're surrounded by our own versions of that spinning sphere. Prototypes in labs, they hint at futures we can't quite grasp. Breakthroughs waiting for the right economic signal, the right material, the right story about their purpose. The lesson of the Aeolipile isn't to dismiss these wonders. It's to ask a deeper question. What world are we building around them? Are we nurturing the soil, the education, the infrastructure, the ethical frameworks? The soil that lets the best ideas take root and grow responsibly, or are we just admiring the spectacle? That ancient bronze orb can leave a dual legacy. First, an enduring wonder at human creativity, the sheer audacity to look at a boiling pot and see not just water but motion, a principle that would, millennia later, carry us to the moon. That spark of curiosity, it's our most precious inheritance, and second, a hard-won wisdom, the understanding that a spark needs more than genius to become a lasting light. It needs a world ready to receive it, a world built with intention. We stand on the brink of new frontiers in artificial intelligence, in biotechnology, in energy, and this ancient story is a compass. It points toward humility, toward stewardship, toward a broader vision of progress, one that values the long, patient cultivation of knowledge. As much as the sudden, dazzling breakthrough, the next revolution won't be launched by a machine alone. It will be launched by the world we choose to build around it.